Hey everyone, on this lecture we are going to see an example of a Markov chain that represents the process of writing a research paper and also the states that are involved. Recall that Markov chains are given either by a weighted digraph, the digraph representation, where the edge weights are the transition probabilities. If I have an edge from the node A to the node B, with a weight of P, this means that from the state A, we will go to the state B with probability P. So a Markov chain can be given with its graph representation, and it can also be given by its transition probability matrix P, which is a square matrix in which the number of rows and the number of columns are equal to the number of states that we have in the Markov chain. Let us take a look at this example, at this Markov chain that represents the process of writing a research paper. Note that in this Markov chain we have both representations, the weighted digraph, and we also have the transition probability matrix P. We can see how we have 4 states. For instance, we have the state of thing, the state of write, the state of serve, and the state of email. Here we can see that from the state thing, we will go to the state serve with probability 0.2, we will go to the state write with probability 0.3, and we will go to the state thing with probability 0.5. The same interpretation we have for the remaining states. For instance, for the state write, we can see how from this state we will go to the state email with probability 0.1, we will go to the state thing with probability 0.2, and we will go to the same state, we will remain in the same state write with probability 0.5. Now remember that from a given state, for instance this state thing, the outgoing edges, okay, the weights of the outgoing edges, that is, the edges that leave from this state thing, they all need to sum the value 1. They need to sum up to 1 because they must form a probability distribution. And this is something that is always true in a Markov chain. We can see here on the state thing, if we sum all the edges that leave from this state, the outgoing edges, we have 0.5, 0.2, and 0.3. And if we sum them, we have 1. In the state serve, okay, we sum here 0.2 that we go to write, 0.3 and we go to email, and finally 0.5 that we go to this same node. Notice that we need to sum this value 0.5 not because this edge is arriving to this state, but because this edge is leaving from this state. Since it is leaving, since it is also an outgoing edge, we need to count it, we need to sum it. Okay, so here we have this Markov chain, okay, with the graph representation, and notice that although the names of the nodes are different than the names of the elements in the set of states, although the names of the nodes are different from the names of the states, this is not a problem, since in a Markov chain the names of the states or the nodes are arbitrary labels. As long as we maintain the correct relationships between the states and their transitions, that is, the edges, including the weights or probabilities associated with those transitions, we can rename the nodes to anything that we prefer. Notice that from the digraph representation it is very simple to see that when we look at the transition probability matrix P, the node thing is the state K, and we know this because of its probability distribution. We can see how in this row we have the probability distribution of the state K, which is 0.5, 0.3, 0, and 0.2, right? So here from the state thing, from the node thing, we go to the same node with probability 0.5, which is precisely what is happening here. From the state K, we go to the same state K with probability 0.5. We go to the node right with probability 0.3. So we can see in here how we go to the state W with probability 0.3. So we can already see how the node right is the state W. We go with probability 0 to the state E. So this is essentially what is happening in here because we go from the node thing to the node email with probability 0. Remember, whenever there is no edge, it means that we go with probability 0. And from this we can see how the node email represents the state E. And finally, we can see here in the graph that from the node think we go to the node serve with probability 0.2, and so the node serve is representing the state S, right? And the same is going to be true for the remaining rows. We can see here from the state right, it is this probability distribution, right? We go to the state K with probability 0.2, which is the node thing. We remain in the same state W with probability 0.5, which is this node right. We go to the state E, which is the node email with probability 0.1. And finally, we go to the state S, which is this node serve with probability 0.2. As we can see, this is very simple. Now, what happens if we are asked the following question? What is the probability that at time t equal to 2, we are in the state K, which is the node thing, if we begin in the state S, which is the node serve? So what is this probability? We want the probability that at time equal to 2, we are in this node thing if we begin at this node serve. How can we compute this? Well, we can compute this if we have the transition probability matrix. And it is very simple. Note that if P is the transition probability matrix and P sub ij represents the probability of transitioning from the state I to the state j in one step, then if we compute P squared sub ij, this represents the probability of transitioning from the state I to the state j in 2 steps. And recall that P squared is the matrix obtained by multiplying P by itself. So, in the solution to this question, to find the probability of being in the state K, which is the node thing, at time t equal to 2, beginning from the state S, that is at time 0 we are in the state S, which is the node serve, then the only thing we need to do is to compute P squared, and then we only look at the row and column Sk respectively. This will represent the probability of transitioning from the state S to the state K in 2 steps. Bear in mind that if at time 0 we are in the state S, of course we know the probability of being at the state K at time t equal to 1. This is the direct probability, the one that we have in the transition matrix. Nevertheless, this is not the probability that we are interested in. We want the probability of being at this state K at time t equal to 2. That is why we need to compute P squared. Once we multiply the transition probability matrix P by itself, then we get P squared, and we only need to look at the position of the row S and column K, and this is going to be the probability that we want. This probability is 0.07. So essentially the probability of being at the state K at time 2, given that we know that at time 0 we were at the state S, is 0.07. Very well, with this we end this brief lecture. On this example, in which we have a Markov chain that represents the process of writing a research paper, as always we remind the student that you can download all of the documentation on the downloadable documents of this lecture.